Welcome to this problem solving session for Structural Dynamics for Civil Engineers, SDOF Systems. I am Lokeshwari. I am a PhD scholar from IIT Hyderabad, and I'll be handling these sessions on Tuesdays from 6 to 8 pm. So, in this week, I will solve some problems. So, every week, based on the concept that has been released so far, and also based on the assignments that were released, I will briefly explain the concept and then we will also solve the related problems. So with that, let's go to the session. So in this course, we are primarily going to deal with single degree of freedom systems. That is, our goal is to find the response of a single degree of freedom system when a dynamic force is applied. So when we are dealing with dynamic loads, along with the system resistances, which is coming from the stiffness of the system, we will also have to consider the inertial effects. So inertial effects are considered in terms of this mass times acceleration terms, which is called as the inertial force. So this is the additional force that we need to consider when we are dealing with dynamic analysis. And first of all, what is the degree of freedom? So a degree of freedom is like how many displacements are required for completely defining the motion or the response of that mass. So here we have, for example, consider this water tank. In this case, this can be idealized as a system shown in this idealized model, where we can assume that all the mass is concentrated here because most of the mass is coming from this water tank, and this column can be assumed as weightless and providing only the stiffness. Hence, this is modeled as a idealized spring having stiffness K. This is one example which can be modeled as a single degree of freedom system. So this has only when there is a ground motion because of the earthquake, there is going to be a lateral displacement for this mass. Hence, in this case, only this lateral displacement is the only degree of freedom that the system has. So this is an example of single degree of freedom system. Now, for modeling this kind of systems or writing the governing differential equations, we have two principles. We can either go with Newton's second law of motion or D'Alembert's principle. So in the case of Newton's second law of motion, it states that the unbalanced force that is acting on a body must be equal to the inertial force, which is nothing but the mass times acceleration. And the D'Alembert's principle helps us convert a dynamic problem into a dynamic equilibrium problem by introducing a fictitious inertial force, so opposite to the direction of the acceleration. This we will see how it is introduced. For example, consider a spring mass system. Which is and then there is an external force F. So when we write the free body diagram for this system, it is going to be F, and then there is going to be restoring force Kx acting on this mass. So D'Alembert's principle says that a fictitious inertial force must be added in the opposite direction of motion, which is mx double dot. So x double dot is double differentiation of the displacement, which is nothing but acceleration. So we can write the equation of motion as mx double dot plus kx is equal to f. So this is one way of deriving this. And in the case of using the Newton's second law of motion, the same equation can be derived without introducing the fictitious force as. So we have the external force F, and then we also have Kx, which is the restoring force. So if this is the positive displacement, positive direction of the displacement, or positive convention for the force, then we have F minus Kx, which is the unbalanced force. This must be equal to mass times acceleration. So again we get the same equation, mx double dot plus kx equals to F. So like this, by drawing the free body diagram and then representing all the forces that are acting on that mass, we can write down the governing differential equations for a given system. So along with this, before writing the governing differential equation, first we have to find out the effective stiffness. So for example, there will be examples of portal frames. Where most of the mass can be assumed to be present here, like on the slab, and the columns can be assumed to be massless and provide only stiffness. And again, this kind of systems can be idealized as a single degree of freedom systems with mass located at the top and having only the lateral displacement degree of freedom. In general, if we do not idealize like this, normally there is going to be 3 degrees of freedom when the columns are fixed at the base. So in static analysis courses, we would have seen that if the beams and columns are axially rigid, then we have 3 degrees of freedom, which is the lateral displacement and the rotational degrees of freedom at the two joints U2 and U3. So we are idealizing this thing to be like this. So with only the lateral displacement degree of freedom, because normally the external loads from which there is dynamic problems arise is like earthquake motions or winds. So they induce those forces are in the direction of this lateral force. So we can idealize the systems like this and then say that this is the only degree of freedom. So for this kind of system, we must find out the force displacement relationship, which is like F is equals to K effective times U1. So before writing the governing differential equation, we must find out this K effective. So for finding the K effective for this kind of systems, we use a method known as static condensation. Let's see how to do the static condensation. So this static condensation is also explained in structural analysis courses, but we will see how to do it for one example. So like I have explained before, this kind of portal frame can be idealized into this system. So this K effective is stiffness in the lateral direction. Although I have represented it like this, it represents stiffness in the lateral direction, and this is the displacement in the lateral direction. So this must be derived by using stiffness matrix method, where we have the force vector. This force vector contains all the forces that are acting at various degrees of freedom in a given structure, and this stiffness matrix has various stiffness coefficients derived for all the degrees of freedom, and U represents all the degrees of freedom of that structure. So in this stiffness matrix we have various stiffness coefficients, so and each stiffness coefficient represent the force that that will be created when a unit displacement is applied at a given degree of freedom and constraining all other degrees of freedom. So that is what a stiffness coefficient means. So we will see what exactly that is. So in this example it is shown that a unit rotation is applied at this end, and then the rotation is fixed everywhere else, and also there is no displacement, there is no relative displacement between these two nodes. So that means only this unit rotation is applied and then all other degrees of freedom is restrained. When this kind of rotation is applied, a moment of 4 EI by L is generated at this end, and then a moment of 2 EI by L is generated at the far end, and then shear forces are generated with a magnitude of 6 EI by L square, which are equal and opposite at both the ends. Okay, these are the forces generated, and in the stiffness matrix this will be represented along a column. So if we say U1, U2, U3, where U1 is a rotation at this node, and U2 and U3 correspond to, in general, a 2D beam element, 2D beam, axially rigid beam, has totally 4 degrees of freedom. Two displacements and then two rotations. So let's say that U3 and U4 correspond to the displacement degrees of freedom, U1 and U2 correspond to the rotation degrees of freedom. Then in this column we have corresponding to the U1 rotation, how much moment is generated. That is what we represent here. And again corresponding to the U2 degree of freedom, that is corresponding to this rotation, we represent 2 EI by L, and then similarly we have minus 6 EI by L square and then 6 EI by L square. So this is how we construct the stiffness matrix. This is for one element. When we are talking about the whole structure, we assemble the stiffness matrices that is coming from each element. This we would have already studied in the structural analysis course. So we will see how to do the static condensation for one example using these concepts. Normally these coefficients, since we would have already derived in the structural analysis course, I am not going into detail how these coefficients are derived. These coefficients can be derived using various methods. We can go with the conjugate beam method. There are examples given in some of the textbooks. So for now we will directly use these coefficients which are already derived and solve this example. So we have a portal frame with columns fixed at both the both the columns are fixed, and the flexural rigidities are given, and also there are for now 3 degrees of freedom. So for this we must first write this relation, force displacement relation, F is equals to Ku. For this we must first find out this structure stiffness matrix. For that what we need to do is we have to apply a unit displacement at each of these degrees of freedom and then find out what is the forces generated. So first let us go with U1 is equal to 1. So when u1 is equal to 1, how does the structure deform? So it is going to deform like this. So here this angle is maintained 90 degrees, there is no rotation here, and this displacement is 1 unit. So when this kind of displacement is applied, what are the forces that are generated? There is going to be a moment generated at both the displacements. So that is going to be 6 EIC by h square. So for the columns, and then again 6 EIC by h square. So, and also there will be shear force generated at here as well as here. So this is going to be 12 EIC by h square, and again 12 EIC by h square. So now we can write down the first column of the stiffness matrix. Since we have shear force contribution from both these columns, the total force is going to be 24 EIC by h square, and then the moment is in anti-clockwise direction, and this is the convention that we are going to assume that it is positive. So 6 EIC by h square and 6 EIC by h square. Now let us apply a unit rotation at this node. So when we apply a unit rotation at u2, the portal frame is going to deform as follows. So here 90 degrees angle is maintained because this is a rigid joint. So when a unit rotation is applied here and the far end is fixed, we have seen just before that a moment of 4 EIC by h, that much amount of moment will be generated. And then at this beam also, because of this unit rotation here, an anti-clockwise moment of 4 EI B by L, which is the length of the beam, will be generated. And then here also, because this is a far end, there is going to be a moment of 2 EI B by L. And because of this rotation, there is going to be a shear force of 6 EIC by h square. From this column. Okay, now we can write down the second column corresponding to u2. So the force that is generated is 6 EIC by h square. There won't be any shear contributions from this column because it's not deformed at all, and the moment that is generated at this joint will be here. So that is summation of moments that's coming from both the columns and the beams. So it will be 4 EIC by h plus 4 EIB by L. And at this node there is going to be a moment of 2 EIB by L. So similarly we can also find out for u3 is equal to 1. That would be very similar to this u2, and we can directly write it down. So we are going to have this corresponds to the force that is generated, the lateral force, that will be 6 EIC by h square, and this corresponds to the moment at u2, and this will be 2 EIB by L, and this corresponds to the moment at u3. So this will be 4 EIC by h plus 4 EIB by L. And this structure stiffness matrix can be simplified for this example by assuming that EIB is equal to EIC. So this matrix will become and also we can take out common EIC by h cube. When you take EIC by h cube as common, we will have 24, sorry, this is h cube, okay, we are going to have 24, and then here we have 6h and 6h, 6h square, h square, 6h, h square, and 6h square. So this is the stiffness matrix for this portal frame. Now we can write down the entire force displacement relation as follows. So we have EIC by h cube multiplied by this whole matrix, 24, 6h, 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 6h square, h square, 6h, h square, and 6h square, multiplied by the 3 degrees of freedom vector u1, u2, u3. This is equal to the lateral force, the external lateral force that will be acting, and then here we have 0, 0 because there are no external forces acting for the dynamic case. So now we can further simplify. So in static condensation, what we are trying to do is we are trying to find out the relationship between the dependent degrees of freedom, which are u2 and u3, and then the independent degree of freedom, which is u1. So in this case, u2 and u3 are caused because of the force that is acting in the lateral direction. Hence there is going to be a dependency between u2, u3 and u1, and they are not independent because there are no external forces acting at those joints. Hence we can eliminate u2 and u3 and then find out the effective stiffness for this. So that can be done as follows. So for convenience, we can divide this entire K matrix as follows. This K delta delta, this can be called as K delta delta, and then this can be called as K theta delta, and then this can be called as, this part can be called as K delta theta, and then this 2 by 2 matrix, this can be called as K theta theta. That means the stiffness coefficients corresponding to the degrees of freedom u2 and u3, and then this is purely because of this u1, and then here we have forces that are generated because of the rotations, and here we have forces that are generated because of the displacement. So we can divide the matrix like this, and then if we focus only on this second row and the third row, then we can write down it as in this matrices we can write this as K delta theta. This matrix is 2 by 1 matrix U1. So U1 plus this 2 by 2 matrix K theta theta multiplied by U2 U3. So this equation is compatible because this is 2 by 1 and then 2 by 2 when multiplied with 2 by 1 we are again going to get 2 by 1 matrix. Hence this is a compatible equation. This is equal to 0. This is 0 matrix because these two forces are 0. Now we have the relation between U2 U3 and U1, so which is nothing but U2 U3 is equal to minus K theta theta inverse K delta theta 2 by 1 U1. So this is the relation that we have, and then we can evaluate the first row multiplied by the first column and then we can see what happens. Now here we have K delta delta multiplied by U1 plus K theta delta which is a 1 by 2 multiplied by U2 U3. This is equal to F. Now we can substitute for this U2 U3 from this equation. So finally we are going to get F is equal to K delta delta U1 minus K theta delta K theta theta inverse K delta theta times U1. So we can take out U1 as common. Now we have K delta delta minus K theta delta K theta theta inverse K delta theta and then U1. So now we have this equation in the form F is equals to stiffness multiplied by the displacement, which is the form which we want, and this term is the effective lateral stiffness. Now we can substitute the values for this particular example and then find out what is the effective stiffness value for this particular example. So let us first find out this K theta theta inverse. Inverse, it can be found out as, so 1 by AD minus BC, that is going to be 35 H square. Six H square minus H square minus H square and 6 H square. Now we can substitute in this equation. F is equal to now we have K delta delta is 24 EAC by H cube. We can write down that EAC by H cube term later and then now eliminate it later, evaluate it later. So now we have 24 minus K theta delta is 6H and 6H. 6H, 6H, and K theta theta inverse is h power 4 here. So we have 1 by 35 h square, 6 minus 1 minus 1, 6, multiplied by k delta theta is 6h, 6h. EIC by h cube multiplied by u1, which means k effective will be 24 minus 6h. So h square, all the h's are gone. 6, 6, 1 by 35. So here we are going to have so 6 6 are 36, so 30 and then 30. Twenty-four minus this can be cancelled out. So once we evaluate this, we will get 96 by 7 EIC by h cube. So the effective lateral stiffness for this portal frame is 96 by 7 EIC by h cube. So by using this method of static condensation, we can find out the effective lateral stiffness, which can be used later during the estimation of the response of this system. Now here is the general equation for this kind of portal frame with varying relative flexural rigidity of the beam and then column. This is a general equation for finding the effective lateral stiffness. And here we have a parameter rho, which is the ratio of this which is represented in this equation, EIB by L to 2 EIC by H. And this graph explains how the natural frequency of this kind of systems vary when this parameter rho varies. That is, when the relative stiffness of the beam increases relative to the stiffness of the column, it shows that the natural frequency of the system increases. So when the beam is infinitely rigid, flexurally rigid infinitely, then we are going to have highest natural frequency of this much, square root of 24 EIC by mh cube. So this is something that we can understand. Now moving on to the next concept, undamped free vibration. So in many of the examples that we will see from here on, they will directly give this lateral stiffness or will ask us to find out the stiffness of the system giving other parameters. So now let's see some of the concept before solving the problems. So we have seen how to write this equation of motion just before, and for this kind of motion is called as free vibration, because in this case there is no external force acting during the vibration, and the mass is allowed to vibrate without any external force just after giving some initial disturbance. So this is the equation, and then this equation is solved in the lecture, during the lecture, hence I'm not going to solve this equation again. And from that, during that time, it's also derived the natural frequency as square root of k by m, K is the stiffness of the spring and M is the mass of the body. So now this equation can be rewritten in a different way. So by assuming tan phi is equal to x of 0 divided by x dot of 0 by omega n. So when we assume like this, we will have sin phi is equal to x of 0 divided by x of 0 square plus x dot of 0 divided by omega n square under root, and cos phi will be x dot of 0 divided by omega n divided by square root of x of 0 square plus x dot of 0 square divided by omega n. This is whole square. Now this equation can be written as x of t is equal to sin phi cos omega nt plus cos phi sin omega nt. So this is in the form of sin a cos b plus cos a sin b. Hence it can be simplified as, rewritten as sin omega nt. There is going to be another term, this term, because there is no this hypotenuse term here. Hence we will have to divide and multiply with this term. So there is going to be this term here, square root of x of 0 square plus x dot of 0 by omega n whole square. So plus phi multiplied by this term, square root of x of 0 square plus x dot of 0 divided by omega n whole square. Hence from this form we can find out what is the amplitude maximum displacement that this mass undergoes from this from the equilibrium position. So this value will become maximum when sin theta value will becomes 1. Hence maximum amplitude will be this value, square root of x0 square plus x0 by omega n whole square. And similarly we can also find out the maximum velocity amplitude. So we can differentiate and find out the equation for the velocity, which will be x dot of t is equal to omega n, this value, let's call it as x max, multiplied by cos omega nt plus v. That means v max is equal to omega n times x max. And also similarly we can do for acceleration. So x double dot t will be equal to omega n square x max minus, let me write this. So x double dot t is equal to minus omega n square x max sin omega nt plus v, which means maximum acceleration will be equal to omega n square x max. And also once we have this natural frequency, we can also find out the time period, which means the time between two peaks or points where the state of the system is same. That is the time period that can be found out using this formula. Tn is equal to 2 pi by omega n. This is called as the natural time period of the system, because there is no force involved or damping involved. Now we'll solve one problem related to this concept. A heavy table is supported by flat steel legs in the figure below. Its natural period in lateral vibration is 0.5 seconds. When a 50-pound plate is clamped to its surface, the natural period in lateral vibration is lengthened to 0.75 seconds. What are the weight and the lateral stiffness of the table? So they have given two conditions, which is when only the table is there and then when a mass is added on the table. So there are, for these two conditions, they have given the natural values of natural time period. So natural time period we have just now seen is equal to 2 pi by omega n, and also omega n is equal to square root of k by m. So this Tn can be written as m by k, 2 pi square root of m by k. Now the first case, there is no mass. This can be represented as 2 pi square root of m by k. In both the cases, the lateral stiffness of the table is coming only from this from these three elements. Hence, the stiffness remains constant for both the cases. Square root of m by k is equal to 0.5 seconds. In the second case, there is another mass added, m plus capital M by k, which is given as 0.75 seconds. Now we need to find out the weight of the table. They have given the weight of this mass as 50 pounds. This is a unit of force. So capital W is equal to 50 pounds, which means capital M will be 50 by G. Now let us divide the equation 1 with equation 2. Now we will have square root of m by m plus m is equal to 2 by 3. We can further simplify this. So m by m plus m is equal to 4 by 9. 9m is equal to 4m plus 4m, which means m is equal to 4 by 5m. So the same relation will exist if we multiply on both sides with g. We're going to have small w is equal to 4 by 5 capital W. Now we can find out the weight of this mass as 0.8 times 50. So this is 40 pounds. Now the next part of the question is to find out the lateral stiffness of the table. For this we will use the equation 1. So we can write m by k is equal to 0.5 square multiplied by 4. So k will be equal to 4 pi square multiplied by m divided by 0.5 the whole square. So this can be written in terms of weight, 4 pi square multiplied by weight divided by g is 386 in inch per second square multiplied by 0.5 the whole square. So once you substitute all the values, so we will get 4 pi square multiplied by W is 40, 386 multiplied by 0.5 square. So once we evaluate this, we will get 16.36. Pound force per inch. So this is the solution for this question. Now let's move to another example. This is a simple example of a beam which is fixed at both the ends, and then there is a mass, there is a weight W at the center, and the mass of this beam can be neglected. Hence we can assume that the mass is concentrated only at the midpoint of this beam. We need to find out the natural frequency of this fixed beam. To find out the natural frequency of this fixed beam, we need to find out, we need to have the mass as well as the stiffness, because this system anyway can be idealized as a single degree of freedom system with lateral stiffness that is coming from this beam. Now we need to find out the stiffness for this beam. That we can find out easily because we know the equation for the deflection, midspan deflection for a beam that is fixed at both the ends, which is deflection is equal to WL cube divided by 192 EI, or else we can say that Y is equal to, here W is not the weight of this beam, it's the external force. WL cube by 192 EI. So we have W, which is the force, is equal to 192 EI by L cube times the displacement. Here we have K is equal to 192 EI by L cube. So we know the stiffness, and we also know the mass, which is capital W divided by G. Hence the natural frequency for this system is going to be square root of 192 EI G by WL cube. This is the answer. We'll solve another example. This example is somewhat similar to the assignment example, which is asked in assignment number 2, but slightly different. Now let's read the question. A mass M1 hangs from a spring K and is in static equilibrium. After this mass is attached, this spring is in static equilibrium. So compared to the unstrained position of the spring, there is going to be some deformation in the spring after we hang the mass. So at this position there is a static equilibrium in the spring. A second mass M2 drops through a height h and sticks to M1 without rebound shown in the figure. Determine the subsequent motion u of t from the static equilibrium position of M1 and K. Now there is another mass M2 which will fall from a height h onto this mass M1. So when it is at a mass, when it is at a height h, so there is going to be potential energy for this body M2 because of the gravitational force. When it is falling and touching this body M1, this initial potential energy will be completely converted to the kinetic energy of this mass M2, and then there is impact on M1. Because of this there will be this kinetic energy is converted to the kinetic energy of this combined mass, from the which we can calculate using the conservation of momentum principle. And also they are asking us to measure the motion from the static equilibrium position of M1 and K. Since there is additional mass M2 which is attaching to this, there is going to be additional force that is going to act on this combined mass, which is the gravitational force acting on this mass m2, which also we need to consider. Now let's see how to solve this question. Now the first thing that is happening is conversion of this potential energy into the kinetic energy of this mass m2. So we have the potential energy of this mass m2 is equal to mgh, which is m2gh, and the velocity of this m2 just before impact, that we can call it as u0, half m2 u0 square must be equal to m2gh. That means the velocity just at the time of collision is going to be square root of 2gh. And also so this is the velocity. Now we can calculate the velocity of this combined mass because of the impact. So they are saying that after the impact this mass is not rebounding. So we can write the conservation of momentum equation as follows. It says that momentum before collision and after collision must be same. Before collision it is just m2 times u0. After collision there is a combined mass with a velocity which we need to find out. So v is equal to m2 by m1 plus m2 square root of 2gh, square root of 2gh. This is the initial velocity for this combined mass, also the initial condition for solving the governing differential equation. And also they are asking us to find out the subsequent motion from the equilibrium position of this. Hence u of 0 is equal to 0 and initial velocity is this much. So let us draw the free body diagram and then write down all the external forces that are acting on this combined mass. m2, this is m1. So on this mass there is going to be a force of m2g, additional force of m2g. We need not consider m1g because we are finding out from its static equilibrium position. I mean this m1g will be counteracted by the spring force. Hence this is not disturbing the equilibrium of the initial configuration. Hence we have to consider only m2g. Now there is a spring force which is Ku. Now we can write down the governing differential equation. If we assume this as a positive direction, we have m2g is equal to minus m2g minus Ku, using Newton's second law of motion, minus Ku must be equal to the inertial force mu double dot. So we have mu double dot plus Ku is equal to m2 times g. Now we have a term constant force on the right hand side. Hence there is going to be a particular integral term in the solution, and the complementary function is going to be same as the what we got for free vibration, which we have seen just before. So we have u of t is equal to a cos omega nt plus b sin omega nt plus m2g by k. Now we have, now if using these two initial conditions we can find out these two constants. Now let us find out the two constants. So u of 0 is 0. So 0 is equal to a plus m2g by k, which means a is equal to minus m2g by k. we can find out B value by differentiating this. So we have u dot of t is equal to minus a omega n sin omega n t plus b omega n cos omega n t plus 0. So we have this much. U dot of 0 is equal to, if we substitute t is equal to 0, we are going to get b omega n, which means b is equal to u dot of 0 divided by omega n. So let us substitute these two constants in this equation to write down the complete equation. So we have u of t is equal to a cos omega n, which is minus m2 g by k cos omega nt plus m2 g by k plus b is m2 by omega n times m1 plus m2 square root of 2gh times sin omega nt. So this is the final equation. So these are the problems, some of the problems that are related till the concept of free vibration. Now let's move on to the concept of damped free vibrations. In most cases, we model damping using viscous damping method. Normally, till now we have idealized that there is no damping, which is not at all ideal. There is always damping in the structures coming from various sources like friction or plastic deformations and other dissipating mechanisms. So these things have to be considered to approximate the realistic situations in a better way. So we assume that this viscous damping is proportional to the velocity, and then it is going to act in the opposite direction of the motion, of opposite direction of the force in a restoring way, similar to the spring force. So this equation is derived in the lectures, so I'm not deriving this thing again. And also the solution of this equation is also derived for various cases. So while deriving this, for mathematical convenience, we have defined few coefficients, which is this damping ratio and the critical damping coefficient. So the critical damping coefficient is defined as CCR is equal to 2 square root of Km. So here K and M are the stiffness and mass, hence this critical damping coefficient for a given system depends on its properties, and critical damping ratio is the actual damping present in the system to the critical damping ratio. So depending on this damping ratio values, there are three possible scenarios, which is overdamped system. We call a system as overdamped system when the damping ratio is greater than 1. So for this kind of system, so the response is as follows, which means after disturbing from its initial position, there is not going to be any oscillation, and after disturbing, it will try to come back to its equilibrium position continuously. And when damping ratio is exactly equal to the critical damping coefficient value, at that time also there won't be any oscillations and it quickly comes back to its equilibrium position. But when the damping ratio is less than the critical damping ratio, then there is going to be continuously decaying oscillations. That means after each cycle there is going to be reduction in the amplitude of the motion. So this is the case under which most of our civil engineering structures fall. Structures have a damping ratio of less than 0.2. So that is why we will focus mostly on the underdamped systems. Now let's see how to solve this equation of motion for the underdamped systems. So using this equation, we can write C is equal to C CCR. So we have C is equal to, now let's substitute C in this equation, mx double dot plus cx dot plus kx is equal to 0, which means let's divide the whole equation with m. Now we will have CCR is 2 square root of km, so we'll get k by m after dividing with m. Now we have k by m times x is equal to 0. So for this equation, the characteristic equation is going to be lambda square plus 2c omega n plus omega n square is equal to 0. So the two roots for this equation are going to be minus 2c omega n plus or minus square root of b square minus 4ac, which is 4 omega n square, divided by 2. This can be simplified as lambda is equal to minus c plus or minus I square root of 1 minus c square. Since c is less than 1, we can take out minus 1 as common. So square root of minus 1 is I, that is what I have mentioned here. So 2 gets cancelled after taking 4 out of this square root. So we will be left with minus c plus or minus I square root of 1 minus c square omega n. So these are the two roots for this equation. Hence the solution for this equation is going to be x of t is equal to, so we have e power a1 e power lambda 1t plus a2 e power lambda 2t. So this will become, so we have this term for the lambda 1 and lambda 2, hence this term can be taken out. So this is going to be e power minus z omega nt multiplied by a1 e power I square root of 1 minus c square omega n plus a2 e power omega n I square root of 1 minus c square. So this term we can substitute with another term, omega d is equal to omega n square square root of 1 minus c square. So this term is called as damped frequency of the system, because in this system it is influenced by the damping. So now if you further simplify the above equation, we are going to have x of t is equal to e power minus c omega nt of a1 e power I omega d, here we have minus, plus a2 e power minus I omega d t. So this terms are similar to the complementary function which we got for the free vibration, hence this can be rewritten as x of t is equal to e power minus c omega nt a cos omega dt plus b sin omega dt. So this form is very similar to the form which we got for the free vibration, except for in the place of omega n we have omega d. That is how we have identified this omega d as the frequency of the system. Since there is damping involved, we call this as damped frequency for this system. Now using the two initial conditions, we can find out the terms a and b. So x of 0 will be equal to, so this is 1, so we will have a, so a is equal to x of 0 and velocity will be equal to minus c omega n e power minus c omega n t a cos omega dt plus b sin omega dt plus e power minus c omega nt times minus a omega d sin omega dt plus b omega d cos omega dt. Now x dot of 0 will be equal to minus c omega n. So we will have just a and then plus so this is 1 and this term gets cancelled, we have b omega d. So b is equal to x dot of 0 plus c omega n x of 0 divided by omega d. Hence we have the equation of motion for the underdamped system as x of t is equal to e power minus c omega nt. A is simply x of 0 cos omega dt plus x dot of 0 plus c omega n x of 0 divided by omega d multiplied by sin omega dt. This is the final equation for the underdamped system. Now, as I have explained before, the amplitude of the motion for each cycle is going to reduce continuously for this kind of system, and we can find out for each cycle how much amplitude is reduced. So now for a time period, so in this kind of we have already seen that the damped frequency is defined as omega n times square root of 1 minus c square, and from this we can also show that the damped frequency will be 2 pi divided by omega n times square root of 1 minus c square, and we already know that 2 pi by omega n is natural time period of the system. Hence the damped time period of the system will be equal to the natural time period divided by square root of 1 minus c square. Now after a time period of Td, let us see how the amplitude of this the displacement of the system is going to change. Now if you see x of t plus td is equal to e power minus c omega n t plus td, and this whole term is going to remain the same, because omega of t plus td means we're going to have the same angle, because that is what time period means. So we can take the ratio of the amplitudes at a difference of time period of td. So if we do that, x of t divided by x of t plus td, so we will get e power c omega n td. Now let us take the natural logarithm. X of t by x of t plus td, this is equal to c omega n 2 pi by omega n square root of 1 minus c square. I have just substituted for td from this equation. Now this is equal to 2 pi c divided by square root of 1 minus c square. So this is the exact equation for this logarithm of the ratio of amplitudes between successive cycles. This ratio is called as logarithmic decrement. And when c is very less than 1, this can be approximated as 2 pi c. And this is a graph which is showing that when we do this kind of approximation, we are not losing anything on accuracy for most of our structures. So for most of our structures, the damping ratio is less than 0.2, and it's very clear from this graph that the two graphs are almost coincident for the two approximations of this logarithmic decrement delta. And it can also be shown that for j consecutive cycles, the amplitude ratio is going to be ln xi by xi plus j. That means the number of cycles between these two, for these two amplitudes, is j cycles. This can be shown as 2 pi j times c. So this relation can be found out in conjunction with the experimental results to find out the damping ratio and other parameters of the system. So the similar kind of relation exists even for acceleration. So there is also similar kind of relation for acceleration. Two pi jc. So during experiments, by measuring out the displacement for a few cycles and also measuring the time period between two amplitudes, we can find out the damping properties and also other properties like stiffness of the system. Sometimes it is convenient to to measure the acceleration of the system rather than the displacement, because most of our structures are very stiff and they're going to have more acceleration, and we will get good signal for using accelerometers compared to LVDTs. And also for LVDTs, to use LVDTs, we need to have a place or a point which is fixed throughout the test, which is not moving. But in the case of real structures, it's very difficult to find out a reference point which is not moving. But accelerometers can be used without that kind of limitations. So based on this concept, we will solve one example problem. A free vibration test is conducted on an empty elevated water tank. A cable attached to the tank applies a lateral force of 16.4 kilopounds and pulls the tank horizontally by 2 inches. The cable is suddenly cut and the resulting free vibration is recorded. At the end of 4 complete cycles, the time is 2 seconds and the amplitude is 1 inch. From this data, compute the following: damping ratio, natural period of undamped vibration, stiffness, weight, damping coefficient, number of cycles required for the displacement amplitude to decrease to 0.2 inches. So now they have given some experimental data where a given water tank, which we have seen can be idealized as a single degree of freedom system, has been disturbed from its equilibrium position by applying a lateral force of this much. So F naught is equal to 16.4 kilopounds. And because of this force, the tank has undergone a displacement of 2 inches. So, and then the cable was cut suddenly, which means the velocity at a time t equal to 0 is 0. So this is some of the data they have given. And also at the end of 4 cycles, that means if you think that u1 is equal to 2 inches, u1 plus 4 is equal to 1 inch. The amplitude at the end of 4 cycles has reduced to 1 inch. And also they are saying that after 4 cycles, that means 4 times the time period, this is a damped time period because there is going to be a damping in the system. So 4 times 2 days, 2 seconds. Now we need to find out the damping ratio. So we can use the logarithmic decrement formula because in that these quantities are involved. So we can directly use that formula. Ln of u1 divided by u1 plus 4 will be equal to 2 pi j. Here j is 4 because the amplitudes are given for 4 cycles apart, and c, which is what we need to find out. Now we have ln of 2 by 1 is equal to 8 by c, which means c is equal to once you calculate, we would get c as 0.028. Now the second part B is natural period of undamped vibration. So from this data we can already find out the damped period, which will be 1 by 2, which is 0.5 seconds. And we know the relationship between damped period and undamped period, which is damped period is equal to Tn divided by square root of 1 minus c square. Now in this we already found out the damping ratio, but we need to find out so we can directly find out the natural period. So it will be Tn is equals to 0.5 multiplied by square root of 1 minus 0.028 square. So once you calculate this, you would get a value of 0.4998, which is very close to 0.5 seconds. That means since the damping is very less, the natural period of this is not affected that much. Now the next thing is stiffness. So we know the relationship. Okay, from this data we can find out the stiffness, because we know the force displacement relationship. K is equals to F is equals to Ku. We know the F as well as U at time instant of 0 seconds. Hence K is equal to 16.4 divided by 2. So this is 8.2 kips per inch, kilopounds per inch. The next part is number of cycles required, the damping coefficient. So the damping coefficient is C, which we have defined in the previous section, which is 2 square root of K times M. So in this we already know the K value, but we need to find out the mass of this system. So mass can be found out using the natural frequency formula. Omega n square is equals to K by M, which means M is equals to K by omega n square. And omega n square can be determined from the natural time period. So here we have time period is equal to 2 pi by omega n, which implies omega n is equals to 2 pi by Tn. Tn is 0.4998. So omega n will be 12.57 radians per second. Now let us substitute this for finding out mass. So this will be 8.2 divided by 12.57 whole square. So you would get a mass of 0.0519. Now we need to find out the damping coefficient. So C is equals to 2 square root of 8.2 multiplied by 0.0519. So after evaluating, we would get a value of 0.0360. Now the last point is number of cycles required for the displacement amplitude to decrease to 0.2. So so they have given that the displacement amplitude must reduce to 0.2. That we can find out again using the logarithmic increment formula. Now ln of initial displacement is 2 inch and then the final displacement is 0.2. This is equal to 2 pi j times c. Now j is equals to 1 by 2 pi, the c value which we got as 0.028 multiplied by ln 10. Once you evaluate, you get a value of 13.28 cycles, which means approximately 13 cycles. Now let us see the concept of Coulomb friction. So in the assignment till this concept there were questions. So with this concept we will close the today's problem solving session. So we will see how the equation of motion varies for different half cycles in this Coulomb friction. First of all, so far we have used the Coulomb viscous damping concept for modeling the damping in our equation, but there is another kind of friction which arises, another kind of damping which arises because of friction between surfaces. So if the mass is moving on a surface where there is considerable friction, this kind of damping arises, and this is modeled using the Coulomb friction concept. We need to model the equations separately for half cycles because this is a constant force that is only dependent upon the frictional coefficient of friction and the normal force. So we will just represent this force as F for simplicity, and we'll see in these equations we can see that the sign for this frictional force changes depending on how the mass is moving. For example, in this B case, the mass is moving from left towards the right side, and we have assumed that this is the positive direction. So in this case, the frictional force will try to oppose this motion. Hence, this is going to act in this from right to left direction. So that is why it is minus F. And other forces is same, which is the restoring force and the inertial force. So this is the equation of motion when the body is moving from left to right, and when it is moving from right to left, this is the equation of the motion. Mx double dot plus kx is equal to F. Now for the case where there is only initial displacement and where there is no initial velocity, let us find out the equation of motion for some half cycles. So for this case alone, we are assuming that u dot of 0 is equal to 0. There is no initial velocity, we are assuming. Now for the first half cycle, let us say that we are moving this body towards some right side and then leaving it. Hence, in the first half cycle, the body is going to move from extreme right towards left, which is this case C. For this case, the equation of motion is this: mx double dot plus kx is equal to F. For this, the solution is x is equal to, we say we'll follow the consistent, x is equal to a cos omega nt plus b sin omega nt plus f by k. This is because of this force, frictional force. Now using the initial condition, which is x of 0 at time t0, we have x of 0 is equal to a plus f by k, which implies a is equal to x of 0 minus f by k. Now x dot of 0 is equal to 0. X dot of t is minus a omega n sin omega nt plus b omega n cos omega nt. This term is 0. So this is 0, which means b is equal to 0. Hence we have the equation of motion when the body is moving from right to left as x of t is equal to x of 0 minus f by k times cos omega n t. So this is the equation of motion when the body is moving from right to left plus f by k. We have this term. So this is the equation of motion. So this is half of the cycle. That means this is valid for time period 0 is less than or equal to t less than or equal to omega by n, pi by omega n, because the total time period for entire half cycle is going to be 2 pi by omega n, which means for half cycle it's pi by omega n. And so unlike in the case of viscous damping, we can observe that the time period of the system is not changed because of the Coulomb damping. It is remaining constant. Only we will see that the amplitude of the motion alone gets reduced for every cycle. Now let's solve the equation for the next half cycle, which is when the body is moving from left to right. So for this case, the initial conditions are going to be the conditions which we obtain at this from this half cycle at the end of this first half cycle. So at the end of this first half cycle, what is the velocity and displacement that this body is going to have? So x of pi by omega n is going to be equal to x of 0 minus f by k multiplied by minus 1 plus f by k. So x of pi by omega n is equal to 2f by k minus x of 0. And velocity will be the formula for velocity is minus a omega n sin omega n times t, because this term is 0, which means that sin omega n times pi by omega n, which means velocity is 0. X dot of pi by omega n is simply 0. Now let's solve this equation, because the sign for frictional force is negative. So for that equation, we will have x of t is equal to a cos omega n times t plus b sin omega nt minus f by k. So let us find out the constants. So x of 0 is equal to a times a minus f by k, and we already have x of pi by omega n is equal to minus a minus f by k, which means a is equal to x of pi by omega n is 2f by k minus x0, which means x0 minus 3f by k, and b will be equal to 0 again because x dot of pi by omega n is 0. Hence we have the equation of motion as x of t is equal to x of 0 minus 3f by k cos omega nt minus f by k. So this is the equation valid from t is pi by omega n less than or equal to t less than or equal to 2 pi by omega n. That means this equation is valid from the extreme left position of the motion to the extreme right position of the motion. So if we see when t is equal to 2 pi by n, the amplitude of the displacement will be x at 2 pi by omega n is going to be omega n times 2 pi by omega n is 1. So we will have x of 0 minus 4f by k. But if we see at time t is equal to 0, the value is x of 0. It is just x of 0. That means at the end of one cycle, the amplitude has reduced by 4f by k. Now let us solve the equation for one more half cycle for the second cycle, which is again from right to left. So again we will just have to find out the coefficients a and b. Again the equation will be same as this equation. So for this we already found out x of 2 pi by omega n. So here this equation will be valid from 2 pi by omega n less than or equal to t less than or equal to 3 pi by omega n. So for this time period, let us find out the boundary conditions. So we have x of 0 minus 4f by k is equal to a times cos omega n times 2 pi by omega n is 1, and then this is 0. We have plus f by k implies a is equal to x of 0 minus 5f by k. Hence for this half cycle we got again x of t is equal to x of 0 minus 5f by k multiplied by cos omega nt minus f by k. This is plus f by k because this is the equation that is valid for this half cycle. So if we calculate for one more half cycle, that is from 3 pi by omega n less than or equal to t less than or equal to 4 pi by omega n. For this half cycle, this is the equation that is valid. So at 3 pi by omega n, let's see what is the displacement. At 3 pi by omega n, displacement will be x of 0 minus 5f by k multiplied by minus 1 plus f by k, which means displacement is 6f by k minus x of 0. So if we again substitute in this for finding out the boundary conditions, we will get the A as x of 3 pi by omega n, which is x of 0 minus 6f by k, let us write down the equation. So we have x of 3 pi by omega n is equal to minus a minus f by k, which means a is equal to x of 0 minus 7f by k. So this is the equation for this half cycle, so which is nothing but x of t is equal to x of 0 minus 7f by k cos omega t cos omega nt minus f by k, which means at 4 pi by omega n the amplitude is going to be x of 0 minus 8f by k. So that means it's very clear for every cycle, for each cycle amplitude gets reduced by 4f by k. So this is important, and using this concept we will solve one example problem. An SDF system consisting of weight, spring and friction device is shown in the figure. So this device slips. So this device slips at a force equal to 10% of the weight, and the natural vibration period of the system is 0.25 seconds. If the system is given an initial displacement of 2 inches and released, what will be the displacement amplitude after 6 cycles? In how many cycles will the system come to rest? Now let's see the equation of motion which we have derived previously for the case of Coulomb friction problem. We have assumed that the initial velocity is 0. So let's see that if that is the case. So they are saying that the system is given an initial displacement of 2 inches and then released, which means the initial velocity is 0 and initial displacement x of 0 is equal to 2 inches. And also an SDF system consisting of so it has a friction device, and the frictional force is constant and it is equal to 10% of the weight, which means 0.1 times W, and the natural vibration period, which means Tn, is equal to 0.25 seconds. So, and they are asking what will be the displacement amplitude after 6 cycles. So we have seen that for each cycle displacement amplitude reduces by 4 times F by K, where F is the frictional force, that is the constant frictional force that is acting, and K is the stiffness of the spring. Now they have not directly given the stiffness of the spring, but they have given the time period of the system, and also they have given F in terms of weight of the system. So using this, we need to write, find out for each cycle how much displacement is being reduced. Now we can write time period Tn is equal to 2 pi by 2 pi square root of k by m by k. And using this, we can write k in terms of k is equal to 4 pi square m by Tn. Again, m we can write in terms of the weight of this mass, 4 pi square W divided by Tng. So we'll substitute in this equation, so which means 4F by K is equal to 4 times 0.1 W divided by 4 pi square W multiplied by Tng. So W gets cancelled, 4. Now we'll be left with all the known quantities. 0.1, Tn is 0.25 seconds, and the units are again in the US standard units, inches, and in these units G value is 386 inch per second square. 386 divided by pi square. So once you substitute this, we will get a value of 0. So here it's Tn square. So we have 0.25 square. So we will get a value of 0.244 inches. That means for each cycle, the amplitude is reduced by 0.244 inches. So after 6 cycles, how much amplitude will be reduced? So after 6 cycles, reduction in amplitude is equal to x of 0 minus 6 times 4 times f by k. So x of 0 is given as 2 inches minus 6 times 0.244. So this will be equal to 0.536 inches. This is the amplitude. This is not the reduction after 6 cycles. This is the after 6 cycles amplitude. And the last part of this question is, in how many cycles will the system come to rest? So let's say that after n cycles, so the system will come to rest if the amplitude is less than F by K. So system will come to rest if the amplitude is less than F by K. Now let's do this by trial and error. We already know that after 6 cycles 0.536. If we count how much amplitude, if we calculate how much amplitude reduces after two more cycles, so it will be 0.536 minus 2 times 0.244. So this will be 0.048, which is less than F by K. So hence after 8 cycles the system will come to rest. That is it for today's class. We will see in the coming week the problems related to the forced vibration motion. Thank you.